All right, we'll start with me walking in the frame. Actually, let me make sure the audio's coming through. Looking good? All right. Okay, today we're going to cover, and try to in one lecture, cover mixed integer programming, and we'll see if we can get through it all. Before I do that, a slight change to the schedule. This is now posted online, but I'm going to be lecturing the next 2 lectures as well on machine learning. We're swapping the machine learning and classical planning lectures just due to some scheduling issues. So no big deal at all, but we're just switching those up. All right, are there any questions? I know there are some questions on the homework, but I think people are mostly resolving those. In terms of the search one, Zach's probably the person to ask about that one. If you have questions on the optimization one, I'm the person to ask on that. So come to office hours, talk to the TA, etc. Are there any questions, though, about general logistics stuff? OK, well, let's just jump right in. All right, so today's lecture is about mixed integer programming. I'm going to start off by introducing what that term is. Actually, who here has heard of mixed integer programming or integer programming by a show of hands? OK, maybe like 25% or something. I'll talk about what it is, and I'll give some examples. For example, Sudoku, which is often framed as the constraint satisfaction problem, can also be written as an integer program. And planning in the presence of obstacles. That's actually a little less obvious how to make that an integer program. But we'll talk about how you can, in fact, do that. Then we'll spend the majority of the lecture talking about how we actually go about solving these things using an algorithm called branch and bound. And what's really nice here is that branch and bound is a really elegant combination of search methods with mathematical optimization. And it's using both these things very, very nicely to kind of get sometimes impressive solutions, though not always. And then we'll talk about some extensions at the end. So let's start off just by saying what mixed integer programs are. All right, so let's recall our optimization problem. The way we formulated a, say, convex optimization problem, we're going to minimize over x some function f of x subject to a bunch of constraint functions gi of x being less than or equal to 0. Remember, we can express equalities this way, too, by just making something both an equality and in both directions, really. So g is less than that, and minus g is less than 0. But we'll write it in this form just sort of to keep notation brief. We'll get pretty complex in this set of slides anyway, even without adding equality constraints explicitly. And our informal view of things so far, at least, was that optimization problems were easy when these things were convex and hard otherwise, right? But of course, the question is, I'm saying hard, and how hard do I mean? And if it's hard, can we still go about finding, say, approximate, global, local solutions, etc.? And for general problems, that can be pretty tough, right? Because these could be very nasty functions. It's unclear, maybe if you can even find a feasible point, for example. That's not entirely clear. And it can be really hard to optimize these things sometimes. On the other hand, when we talk about discrete problems, things like graph problems or constraint satisfaction, we've seen ways in this class so far of solving these things using search methods, right? So we can have some problems which are some graph search problems, which are in general, say, NP hard, but we've yet nonetheless developed search methods like A* that tend to work pretty well, or can sometimes work at least pretty well in practice. So can we bring some of that into the fold when it comes to solving non-convex problems? And the way we're going to do this is we're going to introduce a class of problems called mixed integer problems, or mixed integer programs. And these are a special case of general non-convex problems where we now have 2 sets of variables. And throughout this lecture, I'll refer to these 2 sets of variables as x and z. X are our normal, continuous, nice variables that we're used to handling in the convex case. And z will be our integer variables. So here, x is in Rn, that means it can take on any real valued number, and z is in z to the p, and z, the bold z here refers to the set of all integers. And those are variables we're optimizing over. The constraints and objective are still convex as they were before, but this is still a hard problem. And it's hard, sort of, maybe obviously, but maybe not obviously. It's hard because these z variables here have to be integer valued, and the set of all integers is not a convex set, right? If you have the set of all integers, that looks something like this. Here's 0. It goes the other way too. It can be negative 2, 3, right? And clearly this is not a convex set because this point's in it, and this point's in it, but some convex combination, the line between these two things, is not in the set of integers. So this is not a convex set, and so it can be very hard to solve these problems. I'll quickly jump into a special case of this, actually. It's even more restricted, but which is still a hard problem. Before I do, though, I want to mention there is some ambiguity in the naming of these things. So you may see things called mixed integer programs only if they're actually linear programs with an integer constraint. That was, for a long time, people only cared about linear programs anyway. So the integer case was just called integer programs, but they were only linear programs. Sometimes you will see them called mixed Boolean convex programs for certain constraints sets on the thing, or just mixed integer convex programs. I've heard lots of different things. Mixed integer linear programs is now the new terminology for linear programs that have integer constraints. But just be aware of this. It's not a big deal, and for our purposes, we're calling this a mixed integer program. But if you read other books, you may see something say, this is a mixed integer program, and it's only a linear program. But they aren't that much harder or easier to solve. It's the integer stuff that's hard, not the convex stuff that's hard. All right. And in fact, in this lecture, we're going to focus on an even more restricted subset of these problems, which are called mixed binary integer programs. And this is the same idea. We're minimizing over our x variables, which are real valued variables, our z variables, which are going to be integer valued, but even more restricted, as we'll see in a second. Minimizing some function of these things, subject to a bunch of constraints, and the constraint that all these z variables have to be either 0 or 1. So now, in fact, we're not even allowing them to be all integers. We're just saying these have to be either 0 or 1. Which is nice because now it's a finite set. We sort of can think about ways of solving this more efficiently. We don't really lose that much power here, surprisingly, by doing this. This is still an MP-complete problem, actually. So just in the binary case, this is a very powerful class of problems here. Clearly also still not convex, right? Because this point's in the set, and this point's in the set, but these points in between are not in the set. All right, any questions so far? All right, so today we're going to talk about two things, really. We're going to talk about why this is an interesting class of problems, first of all. That's probably important, right? If we're going to spend all this time solving it, we better know that we can actually do interesting things with it. And secondly, we're going to talk about how to solve these problems using a method called branch and bound. Let's jump right in first talking about some examples of these things. I assume most people here have heard of Sudoku or have done a Sudoku puzzle before. I'm going to try to convince you today that Sudoku is really a simple problem. It's really easy, in fact. Someone called Peter Norvig, who's one of the authors of the textbook we have, has a page on solving Sudoku problems, not with integer programs, but with just search. And he quotes someone and says that Sudoku is a denial of service attack on human intelligence, because it's just taking up all our time doing nothing, just solving these things that computers can do in seconds. So I occasionally do them too. It's a when you're on a plane or whatever, right? They're there. They're kind of fun. But anyway, everyone knows the idea, right? You have these squares like this. You put a number in each of the squares. The rows all have to have unique numbers in them, 1 to 9. The columns all have to have unique numbers in them, 1 to 9. And each box here has to have unique numbers in it, 1 to 9. And typically, we also constrain that a Sudoku problem like this should really only have one solution. If you just made it empty, you could also come up with solutions, right? But typically, you think of it in terms of only having one solution. That's not really important for our sake, though. All right, so we're going to encode this as a binary, mixed binary integer program. All right, and the way we're going to do that, first of all, it might be sort of more intuitive to do things like encode this as a linear program, as an integer program, where each variable is the actual number in that grid there, and they have to go from 1 to 9, right? It actually winds up that things like the constraint that they all have to be different are a little bit harder to represent in that framework. It's a little bit nicer to represent these as a binary integer program. And in fact, the solution times here are typically a little bit faster. So how do I going to do that? Well, I'm going to come up with these variables. These are my z variables. And in fact, in this program, we're only going to have z variables. We're not going to have any x variables. But the notation here gets a little bit cumbersome. Forgive me about that. Hopefully, everything will make sense. Zij is itself going to be a 9-dimensional binary vector. Okay? Zij is, you can think of this as the indicator function of what number is in the ith row and the jth column in this board. All right? And so if this is equal to, for example, to 1, 2, 4, 5, 6, 7, 8, 9. If Zij equals this thing, then this means that that position, the ij position, is equal to 3, because there is a 1 in the 3 location here and 0 everywhere else. These variables can only have one non-zero entry in them. That's a constraint we're going to add, but that's sort of the condition we're putting on it. And that non-zero entry will indicate what value in the grid we have here. So really, there are kind of 3 indices we're talking about here, right? We have I, j, and then if we want to index into this set, we can talk about the kth element of this. This is not equal to that. That would just be equal to something else, right? So there are really 3 indices here, which kind of gets a little bit confusing, but I think this is the simplest way of writing this, so this is what we're going to go with. And for example, here's an example where the 6th row and the 3rd column is a 3, so that has this value here. OK. Now, let's talk about the constraints. This is a set of all constraints that make these things 4 binary variables. Now, we're assuming z is binary. That makes this a valid Sudoku assignment. So I can go through them in each in of itself. So the first one says these have to be 0 or 1 valued, and each square can only have one number. In fact, it has to have one number, though, right? So remember, this guy was equal to, all of these were equal to some vector here. Right? And this constraint up here says every Zij, the sum of all these elements here has to equal 1. OK? So they have to be 0 or 1 valued, remember. The sum has to equal 1. That means only one of them can be 1. Right? If you didn't have the constraint that it would be integer valued, 1 could be 0.5, 1 could be 0.5. Or you could have negative values even if you didn't have those constraints. But because they're binary valued, the fact that the sum equals 1 means that one of these has to be equal to 1. That's constraint number 1. The second one is that if you take any given I, any given row, and sum across all j, all the columns, this has to equal the vector of all 1s. This is the constraint that each row has to contain every number. All right? Because the first one, say this guy here, maybe this. The second one would be some other combination, etc. When you add these all up, they have to equal a vector now of all 1s. Right? That's just saying that the entire row has to contain every number. Similarly, every column has to contain every number. So if you sum over I from 1 to j for a fixed j, sorry, I from 1 to 9 for a fixed j, that also has to sum to 1s. And finally, each 3 by 3 block has to also sum to 1. And I'm writing that as saying if we sum k and l from 1 to 3 for I plus k and j plus l for these indices of I and j, and when I say this means both of these things summed from really two sums here, 1 over l and 1 over j, sorry, 1 over k, and this would be the cross product of all these values here for I and j. So for all these things, this sum has to be 1, 2. And these 4 constraints together for binary z make this puzzle assignment a valid Sudoku puzzle. Now, for any real puzzle, what you would have is you would also have some fixed assignments. Say that the numbers you fix those to be a certain value. So if you know this one is 3, you fix it to be this value. And the other ones you leave as free variables. Okay, I'm not showing sort of the known ones here, but that would be assumed. Okay, so we can take all these together now and put them into a great big program. And I'm writing this actually, so just to show that it does fit on one single slide. But actually, I guess I'm wrong here, because I should also have the constraints that the known numbers equal the known numbers. So this isn't even a quite complete formulation of Sudoku. But it really isn't that complex either. It's some number of constraints. We have a bunch of sums and a bunch of constraints, but it isn't too bad. Or it wouldn't be too bad, rather, except for this constraint here. They have to be 0 or 1 valued. If this was not for this, these are all convex constraints here, and we could solve it without any problem. The other thing I'll mention is that the objective here doesn't really matter, because we're really just concerned about finding an optimal solution, sorry, a feasible solution. There's no real objective when it comes to Sudoku, right? There's no best solution. There's just one solution that's feasible. You have to find it. So here we're minimizing the max over all the sum of the maxes. But the max is, of course, going to be 1. It has to be 1, so it's kind of meaningless. We'll have to choose that specifically because when we talk about how you solve these things, that winds up being a nice solution for some of the modified problems we create. Or sorry, a nice objective for some of the modified problems we create from this problem. All right, let's talk about one more example, then we'll jump into the actual solution methods. And I think I'm giving away one of the homework problems when I say this, so maybe, yeah?
Can you explain the first line?
Yeah, this objective here.
Yeah.
So what that's saying is the objective is the maximum element of these vectors here, all summed up together. Now that's a boring objective because I know what the value is going to be. It's going to be equal to 81, right? Because each one is going to be 1. There's 81 squares. But there's really no objective here. The point is just to find a feasible solution in the binary case. I'm picking that because it will turn out when we modify these problems to solve them, that winds up being a convenient one. But it's really not that important. That could be really anything. It could be minimize z11 and then the first entry of that. It wouldn't matter. Okay, so let's talk about another problem, which is a little bit less obvious. At least it was to me. Let's talk about planning a path of points in space that don't hit an obstacle. All right, so we want to plan a set of points, xi, with each xi being R2. So here xi itself, I'm not using x or y as a thing. I'm using just x to denote a 2D point, a point in 2D space. Get rid of this. I want to plan a sequence of points, xi, from I equals 1 to m. You can think of these as kind of like waypoints to the space, right? These are kind of the points that'll delineate the path. And we're going to minimize, we can minimize a lot of things, but we're going to choose to minimize the square distance between consecutive points. I showed this example when we first talked about robot motion planning. This was an objective that I mentioned as being possible. It essentially encodes smoothness in the path, but we won't worry about the specifics there. And it has to avoid this obstacle. And the obstacle is defined, in the simple case, it'll just be a rectangle. It's defined by two numbers, a and b, where a is the x-coordinate. So a is over here. This is a1. Would be there, that thing. b1 would be the minimum b-coordinate. a2 would be the maximum x-coordinate, and b2 would be the maximum y-coordinate. Am I getting that right, actually? Okay. I might have been swapped these, actually. Let's see. I swapped those. Sorry about that. A2 doesn't matter, but let's go with what I have on my slides. A2 is the minimum z-coordinate, or x-coordinate. And b1 is the maximum x-coordinate, and b2 is the maximum y-coordinate. All right, so the set of all points inside this object is a convex set, right? It's nice. It's a set of all points that are where x1 is less than or greater than or equal to a1, less than or equal to b1, and x2 is less than or equal to greater than or equal to a2, and less than or equal to b2. The set of points that are not in this thing, though, that's not a convex set anymore. That's everything else. And it's obviously not a convex set because you can take 2 points that are outside it, draw a line between it, and it goes to the doesn't stay in that, right? It's not a convex set. So how can we constrain this thing to not go within the obstacle? And I'll write it another way, actually. I'll just write it like this. What we really want to constrain is the fact that we really have a kind of an OR constraint we want to encode, right? We want xi1, so for all xi, we want those to be less than a1, so they're over here, or over here, or greater than b1, or less than a2, or greater than b2. Does anyone see how to encode this as an integer program, a binary integer program? I would never have seen this when I first saw this problem, so don't feel bad. This is a clever trick people have figured out. People at least see the problem. And it's tricky, right? Because you can't multiply x and z variables together. You can't like have the z variables represent, you know, a multiplier on that constraint. Do you constrain it or not? Something like that. It seems hard, right? So here's the trick, and it's called the big M trick. I'm going to let m be some big number, whatever that means. Okay? All it actually has to be is big enough such that the bounds of the space, it's bigger than the bounds of the whole space where we care about. All right, now, suppose z, I'll put indices on z in a second, but suppose just z is one binary random variable, and I have this constraint. I say that x1 is less than or equal to a1 plus z times m. Now's the cool part. So if z is 0, this is the same as the original constraint. It's just saying we have to be less than, we have to be on this side. Right? X has to be on that side. If z is 0. Okay, if z is 1, now we've given ourselves kind of a lot of sort of slack room. In fact, if z is 1, this constraint will always be satisfied because m is big, right? So we're always less than some big number. We can do this for all of them, okay? So ignore this little line down here. What we can do is we can do this for all of them. Create new variables z1 to z4, zi1 to zi4 for each xi. And these are kind of multipliers on these big M variables. Okay? So ignore this for a second. If zi1 is 1, this constraint will be satisfied no matter what. If zi2 is 1, this constraint will be satisfied no matter what. We do the opposite direction. We subtract the big number when we're trying to be greater than something. Similarly, this constraint is always true. If this is 1, it's always true this is 1. Otherwise, it's just the constraints we have. And now is the sort of the clever part. If we have this, then the set of all points that are not in the obstacle is the same as the set of all points that obey this for this sum of these z variables being less than 3. Do people see why that's true? This is sort of the tricks you have to do when you make integer programs, because it's not immediately obvious how to make this an integer program at the beginning, but this is the case. So if these are all 1, this is satisfied no matter what, right? So that's sort of boring, because then we can be within the set and still satisfy these constraints. As long as one of them is not 1, though, we have to satisfy one of these constraints, the original ones without the m's. So as long as this is less than or equal to 3, and we satisfy these things, then xi is not in the obstacle. I did not see that the first time I saw this either. This is a trick people have figured out a long time ago. That's kind of cool, right? Because now we can actually encode being not in a convex set as a set of not convex constraints, because these things have to be binary valued. Actually, but by the way, that also is very important here. If these are not binary valued, then you can make like each 0.5. This is still holds, and this still, you can still be outside. Or sorry, you will still satisfy those constraints even when you're inside, because these are all just 0.5 or something like that, and you satisfy it kind of trivially. So it's only the case when these are integers, 0 or 1 valued, that this is in fact equivalent. Which is kind of, this is nice, because now we started taking these non-convex sets and we're representing being not within 1 as a integer program. Binary integer program, even. All right, so now let's write our final problem. We want to minimize over x and z. This is a mixed integer program, because now we have both x and z variables. Of the sum of squared differences between consecutive steps, subject to all these things being the case for all I equals 1 to m, and x being equal to the start, and x1 being equal to the start, and xm being equal to the goal. Yeah? The constraint says, OK, so this whole set of constraints here just says that xi is not within the obstacle. And the reason we do that is that was sort of the trick, right? That was the trick of this big M, which is just a number, by the way. It doesn't have to be something special about it. It's just some scalar number, a positive number. These constraints together for any I, when these are binary valued, say that this xi is not within that obstacle. So if you have it true for all of them, then you're OK. What's the question over there? Yeah.
So I guess one was, how do you determine how many variables?
You mean how many x's should you need?
Yeah.
OK, right, you're right. That's a good point. Yeah, so in our case, we'll just pick some number, and we'll say that's enough points. I'll tell you why it's actually interesting in this problem. It's interesting in this problem because even though, in our problem, 2 points may lie outside that obstacle, the line between them may still actually lie within the obstacle. So it's actually perfectly valid to get a solution, in our case, where one xi is here and one is here. And in fact, we will get that, because that's going to be a shorter path to the goal. So we're not constraining the line between them to also not lie within that. It's actually a harder thing to do. You can do it too, but it's a little bit harder. So what you can do then is you can actually just have a lot, as long as you have enough of these things, enough x's, you'll get a reasonable approximation to your original problem where they're actually continuous. And so the trade-offs here about how many points you need is a little bit, there's these idiosyncrasies here. In general, it shouldn't really matter, right? Because if there was no obstacle there, it doesn't matter if you pick 2 points or 10 points. it's still the same path. It would be a straight line, right? So the number of points you pick for this particular problem is somewhat idiosyncratic, and it just sort of depends on the specifics of this problem. If you could actually constrain the lines not to lie within it, then you could do it with 2, or rather 3 points. The first one being here, you'd pick one and there'd be a straight line. But that's just because we know the solution happens to have that form, right? So it's not obvious how to do that, I would say. Yeah. Yes, if we're minimizing distance, we'd be in trouble, actually, because the distance, if you did this, put 1 point here and 1 point there, it's the same distance between them, and those points aren't in the obstacle, so everything's fine, right? Squared distance actually penalizes you from doing that. It forces you to have these points closer together. So you still will get this case, because right on the corner, you'll still kind of like try to shoot it kind of closely. But I think these are kind of becoming pretty sort of specific to this problem, that they aren't really the main issue. Not necessarily. So this might still be less cost. Like if you put 1 point right here and 1 point right here, that might be less total distance than this one, than going from here to here to here, going from here to here. So these are sort of very minor things for this specific problem. I wouldn't worry too much about that, but yes. And it depends if you have an even or odd number of points too. So these are sort of minor things that they're not really the main point of this. Yeah.
The other thing was the remaining part of the problem, is that even convex? Just the square part up there?
Yes, that one's convex.
Yeah.
This is a convex. This is a squared norm of an affine term, because this minus that is an affine term. You take the squared norm of that as a convex term. Take the sum of all of them, it's still a convex term. So this would be, that's important. This would all be convex, except for this one constraint here. And that's the character we're going to typically have for these problems, is that they have to be solvable if we didn't have this. Otherwise, we wouldn't really know what to do. Right? Yeah.
Constraints are like for a particular shape of that is clear, right?
Yeah, so you can actually do it for any polytope. You can also, for any set of equalities like this, if your obstacle is defined by that, so it say is some this thing shaped like that, you can do this too. It's a little easier to see for the square case.
Like apparently it seems like the final solution would be a line joining the starting point, one vertex of the obstacle and the
Yeah, so I should also add, this is not the optimal way of doing path planning in a thing like this, especially if you can control your points arbitrarily. Yes, a better way to do it would be to make each vertex of these things a potential point and do a graph plan in that. That's a much better way of doing it. What I will say, though, is this actually is used in practice. And the way it's used is that when you have not just the ability to choose points arbitrarily, but you have, say, some vehicle or something like that with dynamics that are modeled as a convex system, these sort of things actually are very nice. They actually really can encode things like momentum and all this kind of stuff, while including a couple constraints you can't hit obstacles to. So they are used in practice. You wouldn't want to do the simple like point planning problem like this, yeah. Okay. So hopefully I convinced you now that these problems are at least interesting. Now let's talk about how to solve them. All right, let's talk about solving them. And we're going to solve them with an algorithm, as I said, that's called branch and bound. So to start off with, let's talk about the simplest possible way of solving these things. Right? One nice thing about the binary case, the binary integer program case, is that we have a discrete set of total solutions, right? So what we could do is just take, we know that our z's are all to be binary values, 0 or 1. Let's just take all possible combinations of values for them, enumerate all of these, and then for each one, solve the corresponding x. Solve for the optimal x. That would solve the problem, right? Certainly. Of course, the problem with that is that, we had there are p different z variables here. And that leaves 2 to the p possible assignments. Think about Sudoku, right? So Sudoku has 81 times 9. Can't actually forget what that is. 81 times 9, that's a big 700 and something. Possible assignments. That's 2 to the really big number. You're never, ever going to be able to enumerate all of those. And what I'll show you instead is now we'll solve Sudoku maybe and solve it by solving, 20 problems. That was the hardest one I could find. It took 20, actually. The hardest Sudoku puzzle I could find took about 20 to solve with this thing. So this is possible, and it sort of enforces that, that in computer science terms, the problem is decidable, right? We can actually decide, we can solve this problem. It's also actually exponential time, so we know it's at least exponential time. But this is not really a feasible way of doing things in practice. You wouldn't want to do this. That will boil down to Sudoku checking if every possible thing was the case. That would be silly. No one would solve a problem like that. Guess a solution and see if it's right, basically. All right, so let me talk about branch and bound now. What we saw when we talked about discrete problems is that we wouldn't solve a search problem by enumerating all possible paths from the goal to from the start to the goal. We would do some sort of intelligent search. We can do the same thing here. And branch and bound really is just a search algorithm. In this case, it is a best first search. But really, it's actually, because there's no real notion of path quite in the same way, it really is also equivalent to, say, A-star search. It is the same thing applied to finding the optimal Z assignment. So really, you've already know how to implement this for the most part, because you already know how to implement search methods. Now, like all search methods, in the worst case, and like all methods to try to solve an NP-complete problem that we know of, in the worst case, it's going to be exponential, right? In the worst case, it actually is no better than just enumerating everything. It will have to, in fact, the search will have to go through every single possibility and enumerate it. But in many cases, and this is sort of the thing about AI in general, right, is that in many cases, we can do much better. This is much better than enumerating all of them. And in fact, so much better that it's almost silly to even compare those two things. All right. So the key idea of this approach is the following. It uses a concept called a convex relaxation of the problem. What a convex relaxation says is, this problem here, this is our binary integer program, mixed binary integer program. The only thing that's hard about this particular problem here is this constraint. What we could do is take that sort of nasty constraint that has to be either 0 or 1 and replace it with what's called its convex relaxation. So we're going to replace the constraint that has to be 0 or 1 to just that it has to be between 0 and 1. And it's called this relaxation because in some sense what we're doing is we're taking this non-convex set that has just 0 and 1 here, and we're forming the smallest convex approximation to that, which would have to be, of course, the whole set between 0 and 1, inclusive, right? So including 0 and 1. And I'm going to call variables like this that are actually constrained to be between 0 and 1, I'm going to call them z bars. I think I try to keep that notation going throughout the whole lecture here. All right, so that's the simple thing, right? It's sort of the dumbest thing you could do is just say, well, it's a hard constraint. Let's just make it easy. But a few things are important about doing this. The first thing is that if we take this problem and we solve it, this relaxed problem, and we solve it, and we get an integer solution. Okay, so every value of z at the optimal point for this problem is integer valued. It's either 0 or 1. Then we know we've solved the original problem. Does everyone see why that is? Right, because we've expanded the number of allowable points, right? We couldn't, if some point that has all 0 or 1 values is the best solution in this whole set, it's definitely the best solution in this set. This is a smaller set of allowable points than this one. So immediately we have that if we solve this problem and get an integer solution, then that is an optimal solution to the original program. Okay. Secondly, all the solutions to this relaxed problem, that is, any solution we find to this problem, is actually going to be a lower bound on the optimal value of, so it's rather, if we solve this problem, let's put it another way, if we solve this problem, this will be a lower bound on, and you plug it into the f, this will be a lower bound on the true f. So z bar star here is the optimal value where we allow fractional numbers or intermediate values, and z star is the optimal integer solution. This has to be less than that, right? Because, again, we have more allowable points here than we had before. We're minimizing something, so we have to do at least better than we would if we're doing this. At this point now, branch and bound is a really simple algorithm. All we're doing is we repeat the following. And we do it kind of in a search method. So we're building kind of a search. We're building a search tree from this procedure here. We first solve the relaxed problem. Then we look at our solutions and look for one that is not integer valued. Actually, how you pick which one to split on is, you actually can do whatever you want in some sense, but there are better ways or worse ways. We won't really get into that. But you pick one of these things that's not integer valued. If they're all integer valued, you're already done, right? If they're not all integer valued, then you pick one of the variables that is fractional, and you do what's called a split or a branch on this variable. You add one, you explore one branch where you set that thing to be equal to 0, and another branch where you set that to be equal to 1. And you solve these now new subproblems recursively. Don't worry, I'll give this much more formally in a second. This is just sort of the general intuition of what we're doing here. We're solving a relaxed problem, picking one of the solutions that's not integer valued, and branching on this, making one path going down the road where we set that one to be equal to 0, and one path where we set it to be equal to 1. Of course, if you were to explore all these things, you could enumerate all possible combinations. And the leaves of your tree here, you would have nothing but all the actual enumerated solutions. The nice thing about this is we can do the same thing, but apply standard search methods to this, so that we do not end up having to enumerate all the possibilities. And we're going to use, and to do that, we're going to use this fact that that relaxed solution is actually a lower bound. And so fundamentally, all we're doing here is we're taking this approach. We're just splitting on values, assigning them to be either 0 or 1 if they're not assigned in that way in the original problem, and searching based upon that. This is absolutely optimal. I think what you're getting at here is once you take the values that are integral, once you split and assign certain values, to be 1, the ones that were integer valued in the first assignment may not be integer valued in the other ones. So this is absolutely optimal. This is a global search method. It will find the optimal solution, but you will definitely be the case that whenever you solve the problem for the first time, the solutions that are integer valued then may not be integer valued in later ones, or they might be different integer value. They might go from 0 to 1, etc. But this process is just a way of kind of building this search tree over everything. Let me go to the next slide, and hopefully it'll be a little more clear what this actually is. Because what I want to do here is actually describe how this works using best first search, the best first search that you guys know and love and are grappling with on the homeworks, in terms of just a simple search method. OK, so there are a couple things here. The first thing I want to have is this is we have at our disposal a function up there. This is not the function. This part here is the actual branch and bound. This part up there is a function which I'm calling solve relaxation. What that does is that takes as input some set C. And the set C is additional constraints. So what we'll end up doing is we'll put in C, we'll put a bunch of constraints like maybe z1 equals 0 or z1 equals 1. We'll put a bunch of constraints like, or I should say z bar, because we're talking about the ones that are possibly fractional valued. That of course, if we assign them like this, they're not going to be fractional valued. So this function up there takes as input some set of additional constraints, and then solves the relaxed convex problem plus those constraints, and returns the optimal value, the x star assignment, and the z bar star assignment, and also returns the constraints just to make things a little simpler, notation-wise. Okay, so now we have the following procedure. We're going to use a priority queue, which I guess it wasn't really talked about too much in the search, but if you actually implement A star or any best first search method, you should use a priority queue. This is just a list where the top element of that list is always the value with the lowest or highest priority, depending on which way you're sorting things. Right? So you can push values, and what will come off is always the one with the lowest value. In our case, lowest. And what I'm saying here is that if we push this thing, so if we're pushing a whole tuple here, which the tuple is f, x, etc., it's going to order that priority queue by the first element in that tuple. So it's going to order this priority queue by f in our case. This is, by the way, exactly what Python does. So that might be a hint to do that on the homework. Actually, you can do it that way if you want to. You can also maintain two different lists if you want, but it can be kind of nice sometimes have a single list of tuples. OK, so now we're going to start with an empty queue. We're going to push the solution with no additional constraints. That means we're just going to push this original relaxed LP onto our queue. And now we start iterating. Okay, and this is how we do it. We pop off the top element. That's the element that has minimum priority. So that's the element, in our case, with the lowest f value. In other words, the lowest possible lower bound on our objective value. The true objective value, by the way, right? Because any sort of thing for any assignment here will give a lower bound. The relaxation, sorry, not for any assignment here. If you have an assignment that gives a lower bound on it, that is potentially a solution that has objective less than something. Okay? So what we do is we pop this off. That's the one with the lowest f. If this one here is integer valued, we're good, right? We found the lowest possible assignment. It happens, we know our z's that we found there were integer valued, so we're good. We're done. This is an optimal solution. If not, so if it does not happen, we do the following. We choose some I such that this is non-integral, not integer valued, and we push onto our queue the solution with this thing being set to 0 and the solution with this thing being set to 1. And that's it. This is a best first search. And you can think of, in some sense, this f thing here being kind of like the heuristic we use, right, for A-star search. It's lower than for any given sort of assignment, right, for any given set of things like this. This thing here, this f here, has to be lower than the optimal integer value for that assignment. And so it's essentially a heuristic for which one looks the best right now. So we just keep popping off the best one, expanding that one, and doing that. What's nice here is that sometimes we're going to get things here that are really big, or maybe even infinite. Say, once we assign certain things here, we actually can no longer solve the problem anymore. It's very possible. So when we try to solve this, we get f equals infinity. In that case, we're actually lucky, because what that means is we can either just throw it up, we can either never put it on the queue in the first place, or what it really means is that we're never going to pop that one off, because those are infinite solutions. So unless the whole thing's unfeasible, which I guess might happen. But if this thing is infinite that we're pushing onto the queue, it's never going to come back again. So essentially, we're never going to expand it again. We're never going to look at any of its children. And so we've saved a lot of time. That really is the fundamental benefit of branch and bound here, is that we don't have to, if we assign a sense, so maybe it's concretely. Now I have an example of this, so maybe I'm saying this too fast. If we assign this to be equal to 0, we solve the problem, and I'll say only this variable is assigned. We solve the problem, and the objective value is infinite. That means this value, there's no point in trying, what this is 1 and z2 is 0. There's no point in trying that, because we've already found that for the best possible assignment of these things, other values, even ones that aren't integral, we can never do better than infinity. This will probably become a little bit more clear when we go through the example, but that's the basic idea, is that we're discarding a lot of potential enumerations by ignoring those that just aren't ever going to be optimal. Now there's one more point that I want to make, which is actually, if you see branch and bound described, you will probably see this, so it's worth knowing about this. What's slightly more common is that one thing that's kind of annoying here is that we may be in a case where we're really close to an optimal solution in the z, say, but we're just not quite there yet. Maybe it's, one value is like 0.95 or something like this. However, if we just rounded the z to its closest values, we would get an optimal, or at least a feasible solution. And so one thing that's very common is that in addition to generating lower bounds with the method using the relaxations, we also generate feasible upper bounds. And there's a couple ways you can do that, but the most common way is you take all the values of z to your current iterate, you round them to the closest integer value, breaking ties randomly if you have a tie. And then you solve the best fx for that, see what the objective is there, and you've either found a feasible solution or maybe you haven't found anything feasible, in which case you just keep going. The upper bounds can be infinite, but this lets us essentially also generate potential candidates of feasible solutions much quicker than we would otherwise. You actually sometimes can do a lot fewer steps and get a feasible point, rather than, which is sometimes good enough, right? So you can write that in the same sense here. Basically, you can do it in a couple ways. The simple way to do it is just have 2 priority queues, where you actually try to find a feasible solution given the rounded values of your optimal solution here. And rather than terminate when it's integral, you terminate if the feasible solution you find here has objective that is close enough to the lower bound you get. This one I'm just putting it for completeness. You can go through this in the slides if you want. The only real point here, all that we're doing here, is that we're also coming up with an upper bound on our objective for an assignment we know is feasible. And if the difference in objective on our upper bound and our lower bound is small enough, say we don't care about it, then we just terminate and say we're done. Okay? So rather than having to find the absolute best possible solution, we can find something sometimes that's sort of good enough. And by the way, here, if this is true, it is guaranteed to be within epsilon of the true solution, because all these f's here are going to be lower bounds on the objective. So that's all there is to it. This is branch and bound. In fact, this is branch and bound, but what you'll usually see is this one, or something similar to this. The notes I actually linked to were some notes from a different class on branch and bound, which use a little bit different notation here, but it's the exact same algorithm. All right, let's see an example of how this works. Maybe this will make it hopefully a little bit clearer. All right, so we have a simple binary integer program here with 3 binary variables. One objective term, obviously one objective term, and one constraint. Okay, so the objective here is that thing, constraint is this thing here. I'm using this example from, this is the example from those notes I linked to. And it's a nice example because it sort of shows things that can happen as you go down this tree. So let me sort of talk about what happens when you solve this problem. All right, when you're solving on branch and bound, what does the queue look like and what does the search tree look like? All right, so we start off with, we just relax the value. All right, so we have no additional constraints here. We're just doing the pure relaxation, saying that all these terms, rather than being 0 or 1, they have to just be between 0 and 1. Do that and we solve it. When we solve this, we get an objective of negative 0.143 going on. Actually, keeps going. It's not exactly, but that's the value. And the solution we get for z is 0.43, 1, and 1. So this solution is not integer valued. Right? What we do now is we take this solution and we say, OK, this guy here is the one that's not integer valued. Let's do 2 more branches where we do, in one case, we add the constraint this is equal to 0. And in one case, the constraint this is equal to 1. OK, so we're going to add 2 constraints down our search tree. One path says this, we're going to force this to be equal to 0. And then on the other path, we're going to force this to be equal to 1. What we've also done here is we've popped off that first element from our queue. So it's no longer in the queue anymore. And we have 2 more elements. One where the constraint is equal to 1, one where it's equal to 0. Does everyone understand this? What's happening here? The notation here. OK. So let's look at this one first. So this is this branch of the tree. We solve this. So I'm solving this original problem, this problem exactly right here, the relaxed version, plus the constraint that z1 equals 0. Right? When I do that, what I find is that I actually get no solution at all. It's infeasible. So you cannot have that thing be 0. At this point, there's no need to look any further down here. Right? We don't want to care about what can we assign z2, what can we assign z3. It doesn't matter. For this relaxed problem, where we let these be whatever they want, even in intermediate values, we can't find a solution. So we're not going to find a solution if we constrain it to be integers. So we're going to just ignore this. That's all handled, by the way, that ignoring of it is all handled by the priority queue itself. We don't have to actually build this tree explicitly. We can just say the fact that this is infinite, push it to the very bottom of the queue, and we'll never pop it off again. You could even just not put it on if it's infinite, but you can do this too. So this is a priority queue. So the priority queue, the definition of a priority queue is something where the first element is always the lowest value in the queue. The way to do that in Python is just, you can do it, the way you should do it is with a heap. That's the right way to implement these things from a data structure standpoint. With Python, you can just use this as a list and take the min, always look for the min, and call that the top of the queue. When I talk about a priority queue, I always mean something that orders the things by their first value here. OK, so when you push them on, this one goes to the bottom, this one doesn't go to the bottom. Now I solve this problem with the additional constraint that z1 equals 1. And I get this solution, and objective value of 0.2. Again, not integer solution. Interestingly, this variable here, which was integer valued in the first time, is not integer valued anymore. But what we're going to do, that's fine. We're just going to split on this one now. We take z2, and we split on that. We consider the case of z2 equals 0 and z2 equals 1. We go down this path again. That corresponds to this one here. You solve this problem plus these 2 constraints. What you'll find is it's also infinite. That's not a feasible problem anymore. So that one goes to the bottom of the queue. Have the case where z2 equals 1. You solve that. And lo and behold, with these 2 constraints, solving this problem, you get objective value 1 and all integers. So we're done. We never have to test Z3 being 0 or 1, because Z3 here can be anything, and it chose to be 1. So we know that if we constrain it to be 0 or 1, it's still optimal. This is our next property of the relaxation. So now we're done. This is the optimal solution right here. 1, 1, 1. The optimal objective is 1. So integer programming, I mean, it seems kind of daunting, actually. People talk about this as a very complex method, but it's really a simple algorithm. It's just a search method, just like A star is a search method. It's actually even easier than A star because there's no notion of like a path or current cost to the end cost. It's just, everything has a lower bound, maybe an upper bound too if you want it. But it's really a simple algorithm. Now, there are much more complexities you can add to it, but I think it does obscure the fact that it's a overall pretty simple approach. Okay, are there any questions here? Yeah?
Still not sure how we are using the solution of the unconstrained problem.
So, right. So the unconstrained problem, the first one, right? That was this guy here. That was the first element in our queue. But the reality is, once you've solved that problem unconstrained and see that it's not integer valued, it isn't really useful anymore for you. You can't really do anything with it. You can't, for example, just round that and get a solution. We know that's actually not the case because that would be 0, 1, 1. We know that solution is actually infeasible. That's this next one that's added here. So we're not directly using it. What we're doing is we're at every step using a relaxed version. What happened in this last step is we are still doing a relaxation here. We are solving this relaxed problem plus these constraints. But you'll notice we've never constrained Z3. Okay? We're solving, in some sense, still a relaxation of the problem, because the real problem would say these constraints plus Z3 equals 0 or 1. We never have to do that, because we're solving this relaxed version, where now only relaxation only applies to Z3, but still. We're solving this relaxed version, and we get an integer solution, so we know we're done. Yeah? Yes, you can. I have one line on that in the last slide. I'll just say it now, what you do. So say you want Z to be integer valued, not binary valued. You solve that and you find that Zi equals 4.5. Okay? What you do is you split in the same way, but you split with the constraint, or Z bar I. The constraint, actually Z bar I star equals 4.5. You split with two constraints, saying that this is either less than or equal to 4 or greater than or equal to 5. So it's either greater than the seal of that or less than the floor of that. That's actually how you do it in the case of integer programs. We're not going to talk about that anymore. It's one line, the last thing. It's actually not that hard of an extension, but it's just a little easier to see it in the case. A little easier to think about these things and prove that it terminates, all this kind of stuff in the case of binary. There are other things you can do, by the way, too, that are much more complex than this, that you can also do that will. They're much fancier splitting techniques than this, and much fancier ways of actually cutting parts of the solution space out that are very involved, but this works pretty well. Okay. Questions? Any more? All right. So let me take a look at our examples again. Take a look at Sudoku again. So I was looking up Sudoku problems to give examples, with my integer programming solver. And it's actually, I have to say, the hard part of Sudoku is finding problems where the original integer or original linear programming relaxation doesn't work on the first step. It will almost always work right away. So you just relax it, have Z between 0 and 1, you solve the linear program, and you get the optimal solution. Almost always. Not always, but almost always. So I had to look for the world's hardest Sudoku. And this is developed by this mathematician here, and the title, you can't really read it here, but it says, could this be the toughest Sudoku puzzle ever devised? Supposedly this was the hardest, this was like an article in some newspaper. Like, This was the absolute hardest Sudoku puzzle they've made. It's in 2010. And his first hardest one ever came out in 2006. So he spent 4 more years devising the Sudoku problem here to be the hardest one ever. I don't think I could probably, given knowing how good I am at actually doing these, I'm sure I could not solve this myself. What I will say, though, is that my solver, branch and balance, solves after about 27 steps. So 27 different branches, it's solved. And what that looks like is the following. So I minimized my thing. I'm not going to write that whole thing I had on the board before. I'm going to call this, the Z has to be in this valid Sudoku set, whatever that means. That all the rows have to sum to 1, and they have to be, each variable sum to 1. And what we get per iteration is actually an evolution of the lowest variable, the lowest lower bound in our priority queue. Right? What happens is that we keep essentially, we start off with, and there's some integer solution to this thing, and the optimal value then is much lower than 81. We know 81 is the optimal solution, right? Because everything has to sum to 1, or everything has to be 1. These maxes all have to be equal to 1. And what happens is that over time, our known lower bound improves, and after 27 iterations, it just finds the optimal solution. I won't show this tree or anything like that, but basically it's a handful of variables you have to assign. Remember, it's exploring the entire tree, so or all the things that it expands. So, but what happens usually is that you set one thing, and all of a sudden that LP is now infeasible. And very quickly, the LPs, or the linear programs, without the integer constraints, start becoming infeasible. And so you don't have to add very many of them to your actual set. You can just kind of, or rather, I guess, put another way, the priority of those things is infinite for a lot of them. And there's only a few that aren't infinite, and you just solve it. It takes actually, probably a couple seconds, just because CDX pi is not the fastest solver. It's a very generic, nice solver. If you use the sort of a hardcore linear programming solver for this, it would take microseconds, maybe. Probably not. Maybe milliseconds would solve this hardest Sudoku problem in the world. So hopefully that can convince you a little bit that these problems are not worth investing your time and effort into, because you're better off writing a linear program or integer programming solver, and then you can solve every Sudoku problem in the world. All right, let's talk about this next problem too. So this next problem was, oops, I left out some constraints, or rather they just got cut off at the bottom here because I ran out of slide space. That's okay. So we have this problem of path planning the obstacles, a start and a goal location. I here picked the start to be the 0, 0 corner, the goal to be the 1, 1 corner in the Euclidean space, and the object to be a square that's in the middle. You'll see the plot in a second of what it does. I solved this problem, and this one takes a little bit longer. Strangely enough, well, maybe not strangely enough. This problem seems much simpler, right? From a standpoint of actually, what we do. I remember someone mentioned all you do is you just put vertices at each of the corners there, and that's the solution. You can do a graph search over that. That's the solution. So maybe it's kind of sad, actually, that this doesn't do quite as well, and it's a little less impressive in some sense. But I think the advantage here are these cases where you have more complex dynamics of the system that you want to model. So if you're just doing, say, robot motion planning, and you have dynamics of the robot's arm and these obstacles you can't hit, then these kind of techniques are actually quite reasonable. Not everyone uses them, certainly, but some people do use them. The other thing is that there also are better integer programming, or there also are better ways of doing integer programming better than my algorithm here, so you can solve them quite fast. So we do this, and I want to show you what it looks like, though, because this problem here is a little bit weird because we didn't really have an upper bound here, because the reality is it was hard to do anything like round the solution and get a feasible solution, because that would mean we're actually just already at the optimal solution. It is not usually the case that happens in Sudoku because there isn't really an objective. So in Sudoku, there usually is no upper bound when you solve these things. But this problem, there is an upper bound. And I'm going to plot now the evolution of the upper and lower bounds over time. So remember, the upper bound here is I'm taking my current point, I'm rounding the z values, then solving for the x values. So I'm essentially rounding all my fractional z values here, resolving this. What that corresponds to, by the way, is that corresponds to, if it's feasible, as long as these do in fact sum less than 3, that's corresponding to fixing that certain points have to be on certain sides of this obstacle. So essentially what would it say, for example, is that the 10th point here has to be on this side of this and this side of that. Don't worry about the details there, but basically it's just fixing the actual sort of avoidance of certain points in our path. But what I can do here is I can round those variables, and if I get a solution then I know I have a feasible solution to the problem. I have a path that does not pass through this obstacle, because I have these z variables that, when rounded, do in fact avoid the obstacle. And I have I have these x points that do in fact avoid the obstacle, and they have some value. It might not be the optimal value in terms of the objective. In fact, it is not the optimal value in terms of the objective, but it could be reasonable still. So what's happening here is as we iterate, we are cutting off more and more of the sort of possibilities. What this course kind of corresponds to is kind of playing at the boundaries of certain points. Should this point be on this side of the constraint or on this side of the constraint? By the way, a lot of that you can hard code beforehand. So you can actually make this a lot faster if you do things like assume things have to be monotonic or assume things have to be moving in one direction. You can make this a lot faster. But this is sort of just straight branch and bound here. So actually, I think this is straight branch. I might have some tricks built into this to make it a little faster, but this is reasonably straight branch and bound. So again, the blue line here is the lowest element in our queue. The objective for that. Those elements do not have to fix all, or those things do not have to require all the z's to be integer valued. So they're going to be a lower bound on the true objective value. These ones are going to be upper bounds because that we have found them. They are feasible. We know they exist. And this is sort of the kind of progress you see. Little jumps like this in spurts, and then eventually they converge together. I actually don't have a case here, but I should, in the sake of honesty in advertising, I should clarify this is not what you always see. All right? If you're on branch and bound on bigger problems, even with like 5 obstacles instead of 1 obstacle, this case, because that's a problem you can easily solve with the graph method, right? You could see sort of depressing results, right? Where you basically you have your upper bound here, and it kind of comes down like this, and then you have your lower bound that kind of goes like this, and this is a long, long time before they meet. It certainly can be. And in fact, a lot of what the research in integer programming looks at is slightly different algorithms that can accelerate those conversions between the upper bound and the lower bound. If you want to see what this looks like, and this gets back to the issue you were mentioning before about cutting corners, literally, here's the path. So it's kind of depressing, too, because it actually doesn't actually avoid the obstacle, right? If you were to draw a straight line through this, it would go through. But this makes perfect sense, right? Because basically, it can pick, of all these points, the ones that minimize the squared distance. So the best thing to do is to get as close as you can to that without actually touching it. Jump across while you can to make your path a little shorter, and then keep going in a straight line to the goal. This is not actually, also I should add, this is not a completely theoretical problem. This happens in real robot motion planning because checking for collision of points is often much easier than checking collision of entire trajectories or paths through these things. And so it's actually very common to have methods where you have to kind of discretize the number of points finely enough so they don't jump through obstacles or jump through barriers. Because that's obviously the best thing to do, right? So to push through a barrier, get to the solution. So, not quite as impressive as a Sudoku, I'll admit fully, because this is not a particularly hard problem. But this is cool in that it's actually doing now a true mixed integer program, where you have some objective, you have some real valued variables, you have some discrete valued variables, you have a non-convex set you're trying to constrain yourself to, and we're able to solve the problem with this branch and bound technique. Okay, so I have 2 slides left, one on extensions and then one on kind of summing things up. So one thing that was asked, which is a great point, is how do you apply this to integer programs, not binary integer programs? And, well, you do it by splitting on the floor and the seal of the non-integral valued variables you have. I should also add, sometimes, if your variables are both binary valued, or sorry, are both integer valued and constrained, you can represent integer programs directly as binary integer programs. You basically just have a separate variable, like we would Sudoku, you have a separate variable indicating what value that variable is taking. So you can in a lot of cases actually convert integer programs directly to binary integer programs. But if you can't, you have techniques like this that can work too. Yeah?
Wouldn't that be mixing large data?
Yes. So basically you can keep splitting the same thing again and again, having problems. It doesn't always happen. And usually why it doesn't happen is that your constraint set is compact. So you have a finite constraint set that will actually essentially give you similar behavior as you would get if you were to just do the transformation directly from an integer program to a binary integer program by enumerating every possible value. And so in that case, these things can actually work okay too. It's not a high direct branching factor because we're still just branching on two things. Right? Our tree still has a branching factor of 2. It's just that we might have to do multiple splits for each variable again and again, right? So this variable comes back again. Now it's first was 4.5. Now it's 5.5. That happens actually less than you might expect, though, because if it's 4.5, it wants to be 4.5, and so when you constrain it like this, chances are one of them will hit the boundary. It isn't guaranteed certainly, but it tends to happen that way. In fact, oftentimes both of them hit the boundary. So it certainly can happen, but it's not a horrible way of doing it. But that being said, there are much more advanced methods, including the notions of cuts that cut out some of the space but leave all the integer solutions. This leads to a method called branch and cut, which you may hear as well. Don't worry about it if you do hear it. It's just essentially like this, but with slightly more advanced, or sometimes even less advanced, because they don't even split. They just do one cut. But it's just a slightly different way of doing these very similar things. The last thing I'll say is to speed these things up a lot. Oftentimes, you want to make solvers more efficient at solving a given problem by essentially starting at good points. So maybe previous points are good initializations for future solvers. So I have some final words here, but in the interest of time, I'll just say that these are cool methods. They work sometimes really, really well, can make you do much less search than exhaustive search. They're really intelligent, but they're also problem dependent. And sometimes some integer programs you can solve. These are still NP-complete problems, so tread carefully. All right.